So we were working on the thickness lemma. Well, as to say, we had formulated the thickness lemma and maybe just a little bit more, but certainly improved it, yeah. So what did it say? It says, well, if you have a C which is CE non-computable, if you have a B which is CE such that any finite number of columns of B do not suffice to compute C. That doesn't mean that all of B doesn't suffice, but at least any finite number of columns doesn't suffice. Then it is the case that there exists a CE set A, which is a thick subset of B. So in general, all we care about is that the columns of A are, I'm going to say this wrong again, for every column index, that column is almost equal to the same column for B. But for certain arguments later on, we definitely want what's suggested by this inclusion as well, that A is a subset of B. Which our construction obviously does, because the construction, which will appear again in a moment, was if something appears in B, do something and then maybe put it in A. So you're never going to put something in A which is not in B, therefore this subset relation is automatic. Such that A Turing reduces to B, which we didn't care in the least about for the last purpose, or for the purpose we introduced this lemma for, but it's true and it'll be useful later. And C is Turing reduced. Oh, I guess I didn't fix my notes. C is not computable from all of A. This is the essential improvement. From B to A, the essential improvement is that instead of not being computable from some number of columns, it's not computable from the whole set. Okay, so we already have decided on the requirements. The thickness requirement, the eth column of A should be almost equal to the eth column of B, and I pointed us exactly that this means that whatever was computable from these eth columns of B is computable from the eth columns of A. The eth computation does not compute C from A, and this other thing, A being Turing computable from B, needs to come from somewhere else. Then, in order to do this construction, we had the usual definition of length of agreement, but a length of agreement and then an improved version of I guess maximum length of agreement or something like this. Right? M measured all agreements that ever have occurred before S, where the computations haven't gotten messed up in the meantime. Right? Not just the agreement is still the case, but the agreement is the computation that once computed the value on the A side, and at that time agreed with C, that computation hasn't changed, even though maybe C has changed, but that computation hasn't changed. So this is the length of agreement version we're using. Whenever you see an agreement at some point, you're going to keep protecting that agreement, even though it might not be an agreement anymore, as long as the computation hasn't changed in any way. And for the same kind of reasoning, we introduced already these hat notations. And the hat notation was exactly about, well, it computes exactly like the unhatted version did, but then after you have computed this, you check, well, has the use been stable for at least a moment? Right? So the hatted version of this computation is equal to the usual version, as long as then after the fact you look at the use, and if the use just changed, then you don't trust this computation yet, and you make it undefined. That was exactly the point of these headed versions, because we don't want to deal with the situation where you have a computation defined to be one value, you mess up the computation, but by messing up this computation, immediately another computation exists that takes its place, and then later on you mess up that computation, and immediately a different computation comes in to take its place. We want to make sure that whenever computations get changed, there is a moment of undefinedness in between. Right, that was the point of the head computations. Everybody happy with that? This is I guess it's hard to see now, but after we've done the proof, you'll see this is kind of an important idea in the whole proof. Well, and the importance relates to. I forgot. I should have written down here. Well, I'm not sure actually what good it does. I don't want to write down the whole formulas, right? I already did. But the restraints are exactly what you expect them to be. The restraint derived from M is just all the computations that were, all the uses of all the computations that were involved in these agreements are what you want to preserve. And then the capital R is the maximum of all the restraints of this requirement and before. And that is, right, you want to take all of them into account at the same time, because we are no longer going to get that the limit of these restraints exists and is finite, but we are going to get that they drop down every now and then, and by studying this R, you ensure that you observe the times when they drop down simultaneously, all of the requirements at the same time. Okay, so the construction is exactly what you expect to happen now. At any time, at any stage, you look at all the elements that are in B, and you look at, okay, which of these elements are in a certain column of B and above the restraint associated with that column. And if it's in a column and above the restraint associated with the column, you stick it in A. Whether or not the element just appeared in B, because you want to keep looking, because I guess I already said that, but it's kind of a key factor. Right? Before we had these constructions, something appears in B and you immediately decide where to put it. You can't do that now because you possibly have to wait until the restraint drops down. And this is why at any stage you consider all the elements that are currently in B to see if you can stick them in A. Okay. Then we have the true stages. This is sort of well, I guess this is the flavor of infinite injury we're currently looking at, the strategy using true stages. And the true stages one, there's true stages for different kind of sets that we have, but in particular we consider true stages for A and true stages for the first couple of columns in A. And what is a true stage? A true stage is where you enumerate something into this set, such that never later something smaller appears. Something smaller never... it's obvious what I'm trying to say, right? You enumerate some... This is the smallest element that will ever appear past this point. I think that's true too. Do you know what I mean? Or should I actually... Right? The definition is easy enough. AS is the least x such that x is in as minus 1, 0 if it doesn't exist, and the true state is one where a up to as is equal to as up to as. Right? After this stage s, nothing will appear in a that is less than as. Right? And so there's two things obviously true about this. Well, there is one thing obviously true about this, and that is that if A is a CE set, then there are infinitely many true stages. Because you start enumerating, and you enumerate some element. Now either this was a true stage, or something smaller will appear later on. Now either that is a true stage, or something smaller will appear later on. And well, the natural numbers are well founded, so you can't have an infinite decreasing sequence of natural numbers, so you find a true stage above everywhere. And right, this goes for the CE set A, but it also goes for the CE set, which is the first E columns of A. So there are infinitely many true stages, but during the construction you never know if you are in a true stage. Right? So the true stages are most of the time a good analytical tool for analyzing the construction. You can say, okay, we are at this time now, go to a later time which is a true stage. You can't effectively do that, but you can do it in the proof about these things. Okay, so what is the key effect of these true stages? We have these head computations, and we're going to pretend, whether I say so or not, that any computation is a head computation. Right? Just because it's more convenient, and if I were to try to write the heads everywhere where they should be, then well, 0% probability that I'd get that right. So whenever I need it, it's there. So whenever I have phi e a of x at some time t being equal to y, so this is what you would say, this is an apparent computation at time t. And it's apparent because a is going to change and might ruin the computation. But if you have this, and t is in t, right, and you are at a true stage, then this apparent computation is a real computation. Right? And this is not really the actual conclusion I'm making. It's not just the case that if you compute something at a true stage, then you will compute the same output value in the final stage. The computation also stays the same. Right? An actual computation, and here definitely for emphasis put the hat on here, right? If this hat computation converges, then that means that the use of this computation is completely contained in the initial segment, determined by the last element that was added, and this initial segment, because the last element that was added, because this is a true state, this initial segment will never change, therefore the computation is forever preserved. So in particular, what you also get is that if we have something which in the end diverges, right? In most of our constructions we have had these analyses of saying, okay, if in the end it diverges, it means it might converge infinitely often, but change all the time. Well, that's still true, but it certainly means that for every true stage, this computation diverges, right? Because if it ever converges as a true stage, then this computation is forever preserved and you keep it. So at a true stage, everything diverges, which will eventually diverge, but of course not everything needs to converge yet. But whatever does converge corresponds to final, real, proper, honest computations. if you want to, I already told you I'm not going to succeed at it, and I'm trying anyway, but there's clearly a hat here, right? The non-hatted version might converge just fine. Also here, I guess you can observe that as soon as you converge at some true stage, then you converge at all later stages, in particular at all later true stages. Right? Nothing happens because the use just... being a true stage means the use has stabilized. And that's the only way things could go wrong with a computation if the use changes. Okay, so then from this we get monotonicity properties. What do we want to, well, what kind of properties do we want to get? Well, we want to get a handle on our length of agreements and restraints. And the monotonicity properties are the ones that give us some handle on this. So it is the case that for every true stage and for every S that comes later, the length of agreement at the true stage is less than or equal to the length of agreement, or this maximum modified length of agreement at any later stage. Because all the computations that we didn't purposefully make diverge by the hat trick at the true stage are permanent forever existing computations, and therefore in particular they still exist at this later time S. And the modified length of agreement was exactly right. It didn't care if the agreement disappeared as long as the computation didn't change. And so this MES includes all the agreements that we had here, because these agreements, the computations haven't changed, so you keep them. Well, from that, then you get that the restraint can only go up, right? Because these computations that are still here to include in the modified length of agreement, the computations haven't changed, therefore their uses haven't changed, and so all the uses that you are protecting here are also things you're protecting here. So this is more than anything a warm-up to the next lemma, which is the second monotonicity property, which says that if A, let me be very brief, is constructed from B and C by the thickness construction, right? If the A is in fact obtained from B and C by the construction we've described before, then more is true, because then we can say for every TE true stage, so what is a TE true stage? This is a true stage for just the first E columns of A. So this is a stage where smaller things might later appear in A, but not inside of these first columns. And if you look at the product and you have some element here in the product, then the things which are less than or equal to it in the ordinary order might be something like this, and so stuff might be enumerated over here. I don't know which bijection you took between the natural numbers and the pairs of natural numbers, so I don't actually know what this looks like, but you have something nice like this. Later stuff might appear in here, but not in these first E columns. And this last element, of course, doesn't need to be enumerated. It can be enumerated everywhere. It should be on this line at least. right? Later stuff can appear here, but not here. So this is weaker than, certainly an actual true stage for A is a TE true stage, but not the other way around. So for each of these true stages, and for every S that comes later, we get the same conclusion. The length of agreement that we had is forever preserved. It's increased, or it could increase later, but it can't decrease. The restraint can't decrease, and because a true stage for the eth column is also a true stage for the e minus first column and all earlier columns, you get the same thing for all the earlier restraints, and therefore you get the same thing for the maximum. So this is why the true stages are important for us in the construction. They are, right? But we cared about points where the restraints all drop down at the same time. Well, if they are going to drop down, then they drop down at the true stages, because you can't go lower than what happens on the true stage. Oh, why is this true? Well, this is true, right? If I look at this length of agreement, there are certain computations involved. Well, the uses of these computations, they also look like things like this. Right? The use of the computation. And now there is two things going on. Well, first, here nothing will appear because it's a TE true stage. So that means that the higher priority requirements, the requirements that get to ignore this, whatever this eth requirement desires because they're higher priority, that could just enumerate in here whenever they want, don't, because it's a TE true stage. And the lower priority requirements, they only enumerate above the imposed restraint, and so they don't enumerate in here. Because that would mean, if a lower priority requirement enumerates in here, it would break the restraint, and our construction doesn't do that. And this really is sort of the key effect of our imposing of restraints in this construction. That you just need these true stages to have this monotonicity. And I'm emphasizing that now because in the remainder of the construction, at some point you're going to wonder, why isn't he saying more about the restraints? They, before in earlier construction, seemed to be very important and be mentioned all the time, and now he's mostly quiet about them. It is because here it is. This is mostly the key use of the restraints. The fact that this part of the use is automatically protected by the construction, and therefore that we don't really need true stages, we just need true stages for numbers of columns. Okay. Proof. Of this thickness level. We have analyzed a lot of we've analyzed a lot of the ingredients that go into our construction, and now we're ready to prove it. And of course, yes, we're no longer doing finite injury, we're doing infinite injury now. But the proof method is going to be exactly the same. We assume by induction that the things we want are true for all higher priority requirements, right? The higher priority, I guess I never introduced a total order of these requirements, but here you can conclude what it should look like. Right? We assume that the higher priority nj have succeeded. There's real differences there. We assume that the limit over the true stages of these restraint functions is finite, which says nothing about the limit over all stages, because between the true stages it can jump a lot, but those are fake computations that get ruined at the next true stage. And the PJ have succeeded so that the thickness happens. And I could just as well write this column is a subset of that column, right? Additionally. Okay, and so now the inductive proof has to, from these assumptions, now show that these three things are true for E. So we need to see that NE, which is phi EA, is not equal to C. Did I wait long enough? Clearly true, and clearly true by the same strategies we've applied before. Well, I have to be sufficiently careful, right? Before, when we had these kind of requirements, how did we show what happened? Well, you said, suppose they are equal towards the contradiction, right? We know that C is complicated. In particular, C cannot be computed from the first E columns of B. Therefore also, C cannot be computed from the first E columns of A, because by induction we had already assumed that they were the same. And before we said, okay, now suppose they are equal, then the length of agreement shoots off to infinity. And if the length of agreement shoots off to infinity, then in order to compute C, what we do is we look for a stage where the length of agreement is longer than this particular value. This exists because the length of agreement goes off to infinity. And because now that computation on the A side is forever preserved, and they are equal in the end, C needs to be equal to whatever you just computed on the A side. It seems convincing, right? Almost I could say, that's it. Now if you carefully think back to all this talking I did before finally starting with the proof, then you realize that this is not quite it, because we have an infinite priority, infinite injury argument, and so whatever length of agreement we have, we cannot presume that it will be forever preserved. There's infinitely many injuries. This length of agreement goes up and down and up and down, and so length of agreement at some point might go past the value we're interested in, and then later drop down, the computation got ruined, and then a different value gets computed for the next time the length of agreement goes above this. However, we are saved because right? C cannot be computed from the first E columns of A. Therefore, because these true stages are equivalent to the E through stages, or the set of E through stages is equivalent to this, it's enough to show that C cannot be computed from these E through stages. And now we win, because what we look for is a time which is the least stage which is E true such that P is less than MES. But we're trying to decide what is the value of C of P. Is P in C or not? What we look for is the first time that we are at an E true stage that this length of agreement is past the point we're interested in. And because it's an E true stage, all of these computations are forever preserved. Second monotonicity property there, and therefore what we compute on the A side really is the value of Cp under the assumption that they are equal. And then you look at this expression here, and you notice that this T is computable in TE, therefore computable in the first E columns of A, therefore computable in the first E columns of B. Contradiction, because C should not be computable in the first E columns of B. So you notice the argument is exactly the same as your length of agreement arguments before, with the one additional ingredient that we have these E true stages. Everybody happy? Okay, then we need to see that RE, which I define to be the limit over T of RET is finite. First, of course, when you see this kind of expression, you should rightly worry for a second and say, okay, you define R to be this limit, but does this limit exist at all? Well, yes, the limit exists, because I'm not taking the limit over all stages, in which case you should definitely not believe the limit to exist, because it's going to fluctuate all over. But monotonicity theorem, or lemmas, say exactly that this over the true stages is strictly increasing. Therefore, either it exists and has a finite value, or it exists and has an infinite value, or does not exist in the particular way that it goes off to infinity. I don't know. I don't know what I teach you kids these days about the limit going off to infinity, if that means it exists or not, but I think it exists. Do you think it exists if it goes off to infinity?
Yeah, calculus students don't.
Calculus students don't.
Because we tell them it doesn't.
Yeah. I tell them it does, but I think I say it exists, but it's not defined.
Oh, that's even worse. Anyway, so we all agree with this, right? I can define this. The only worry is does it goes off to infinity or not. Okay, but we do things in the right order. We first show that they're different. So now we get to assume we have already that phi E of A is not equal to C. right? We know they're different. Therefore, we can also define PE, which is the least x where they are in fact different. Right? They are different, therefore look at the least place where they are different. Well, one of two, 5 minutes. Well, one of two things happens. This value diverges, in which case it diverges at all true stages as well. Right? Or, amazingly enough, this value converges but is different from the value of t. Okay, so then what do we do? Then we say, okay, right? In both cases, we can certainly go towards a stage where all the computations below PE have converged to their final values. Right? There's finitely many computations there. There's finitely many computations on the A side. All of them converge because right, the least place where they're different can certainly not be bigger than the least place where A diverges, because C certainly converges. So all of these converge, go to a stage where all of them converge. Plus, if possible, this one converges, and that also has achieved its final value. Right? So this part has everything up to and including this first difference has stabilized, except of course that if it diverges, every now and then it might converge, but not at a true stage. It might converge and then diverge again. So now if we look from here on out, you notice that all the computations are real computations. They're not going to get ruined. So from here on out, the only things that are going to happen is, at this particular stage, it might be that our current maximum length of agreement is longer than it should be, because there might be apparent computations above this least difference, which seem to be equal. So from this stage on, the length of agreement at true stages can only go down. Because at true stages, these computations that are fake are going to be thrown away, and this true difference is always there. Therefore, the length, the length of agreement from this point on will never go above PE, but the length of agreement earlier might have gone above PE, and there might still be some of these computations preserved. These computations could be ruined, but you never capture any new computations, because this difference is going to be forever there. Therefore, the length of agreement can never go past this point again. Therefore, M goes down at true stages, therefore the restraint is taken care of. Well, really, at the next true stage, all of the computations get killed that couldn't be killed, and you're good. I can't believe I'm going to get this far in the proof and not finish it. properties here I don't have to say anything about. Right? Our restraint, the limit of the restraint at the true stages exists and is finite, and therefore our construction that says whatever you see in the eth column of B, if it is above the eth restraint, put it in A. Well, that works for everything above this final limit value. Everything that appears in B will appear in A. The final limit value is finite, therefore the difference between these two is also finite. Right? So the whole construction was set up for that. Okay, so we did not finish the thickness lemma because we still have to conclude that A Turing reduces to B. And I cannot think of a -1 minute length proof of this fact or explanation of it, so I'm going to leave that out for next time. I'm not going to build up the whole construction again next time. I'm just going to pretend we are exactly at this time and everything is fresh in your mind, so that's your responsibility. But at the very least we proved the theorem we were working on this lemma for, because that didn't use this fact at all. Right? So we proved enough of the thickness lemma to prove the theorem we used to introduce the thickness lemma. The next time we'll show that A Turing reduces to B.